pleasure to introduce Professor collaborators and who's been collaborating with myself and Lou, well, mainly Lou, for a long, long period of time. I think we met in 94 or 95, but I'm sure Trond remembers better. And yeah, it's been quite an adventure. And Trond has been the director of a Center of Excellence in Oslo, the Center of Earth and, I forget what the full name, Earth Evolution Dynamics, SEED. We all got seedling t-shirts, that was very sweet. And then he started another Center of Excellence on planetary habitability, which was funded, and he's still involved with that, and he's given the reins, or he's passed the reins of leadership on to Stephanie Werner, and so now he has time to come and visit us. And I hope we keep up our collaboration with Trond and fun and adventures as we go forward. So over to you, Trond.
All right, thank you. As Sue said, I've changed my agenda into plant habitability. I'll say a few words about it, but I selected this title for a reason you will see on the next slide, because it's something I used to work with both Lou and Sue and Kevin Burke, who also used to be honorary professor, at least from 2004 to 2007. So I talk a little more, so I don't really work with these things any longer. It's about 10 years since I published on it and moved on, but at least I tell you a little story of what we figured out. And the reason I'm here is because of Lou. So we met in 95, that's the year. And I spent last night for the first time alone in the house without Lou, but I felt he was there. We felt the presence of him, so it wasn't that tear dripping. So we felt it, he was with us. And in the bookshelf, I saw these, you'll know he was a great scientist, he was an A-rated scientist. I saw 3 of these from the Research Council, but then Sue showed me, actually has 4 times we got A-rated. It was 3 times A-rated here at Wits, and before that, it was used to call RAW. But I guess it got degraded once and had to go up. But he's one of the few. I guess there's only one other in geoscience A-rated, so he was a great scientist. So I'll say a few, I will dwell into that. And I also checked. Actually, I found out that me and Sue are the one to publish most with Lou. So I have 29 papers published with Lou. And we have one in the pipeline, which Ben has to fix at some point, hopefully. So at least we do the honor and finish the paper. And so 2 of the papers, maybe most important with Lou and Sue, was a paper in Nature in 2010, diamond samples by plumes from the core-mantle boundary, and a lot of people read it wrong. They said diamonds doesn't come from the core-mantle boundary, and we didn't mean that either. They are taken up by plumes coming from the core-mantle boundary. We actually got a comment on that from a misunderstanding. And another important, actually, to use what we knew about large igneous province and kimberlites, how they erupt and how they interact with the surface processes. But what I consider actually the most important, but it's not that much cited compared to the other one, deep metal structures are reference frame for movements in and on the Earth. So we can use this as a reference frame to reconstruct the continents. So this is the last picture I'm on with Lou. This was in 2024 after his 75th birthday when I was leaving for the airport. So that's the last photo we are documented on. So I'll say a few words. I now work with planetary habitability, and particularly on the time dependence of habitability, because Habitability is very time dependent. We live now in an oxygenated atmosphere. We only got that 2.34 billion years ago, but we started with an helium hydrogen atmosphere. We got a secondary atmosphere from the magma, which was probably very rich in greenhouse gases like CO2. So that's what I really try to work on now, is to understand how much CO2 did you actually need it in early Earth to compensate, because the sun was dimmer by about 30%. So when you look at our position today, Earth is the only of the terrestrial planet in the habitable zone. But it wasn't exactly like this when the solar system was formed. So, and the other thing I like to, if we talk about habitability, Earth is the only one in our solar system with advanced life. And as I told during coffee break, you might find a dead bacteria on Mars, and that will be it, okay? So that's what I say. Earth is the only eyewitness to planet habitability. And there are a few unique things which makes us different from all the others. We have abundant surface water. Mars probably had that, maybe also Venus, but on Venus it's probably evaporated quite quickly. And Mars got pretty dead at about 3.7 billion years when he lost the water and the atmosphere. So we are unique there. What I didn't know when I got excited about it, we are the only one with a large moon. It's actually stabilized the rotation axis, controls the length of the day, which is trained dramatically. It's slowing down from 6 hours during earlier to now 24. And we also I emphasize long-lived magnetic field. We are only of them as a long-lived. Mars had a field, strong field, but also gone early. Venus doesn't have a field, probably never had it. Mercury, practically no field. So that's a third, very important. And we have plate tectonics as well. So maybe we needed all these ingredients to actually to sort out the surface motions. And some of the things we're also working in the center when we call about environmental drivers, you can see they vary from very slow, the changes in the sun strike to impacts. And you know, the biggest impact was the moon forming event. Probably happened about 50 million years after Earth was formed. And there is a whole range of others, like changes, you can see the time length scale, changes in the length of the day, which has to do with the moon going slowly away, and also changes in plate tectonics. And the one I put in yellow here are relatively unique to our planet. And also changes in the magnetic field are on shorter time scale. So I showed in the beginning, we are here today after 4.567 billion years. But if you take the present atmosphere, and we have if you're worried about global warming and high CO2, we actually have ridiculously little CO2 if you look in Earth history. So in terms of, we are closing into 500 ppm, which is about 0.05%. But if you project that backward, because the sun was dimmer, you see Earth would be too cold also Mars. We were actually outside the habitability zone. So that's some of the thing I'm interested in now. And one way to compensate for that is to have a very greenhouse saturated atmosphere. People have talked about 50, 60, 70%. I think we don't need more, about 10, 12% is enough to do this. So when it comes to the magnetic field, we all know it protects us from high energy solar particle, cosmic rays, and can also do biomolecular damage. Also, some arguments how much is modulated atmosphere. Some people say if you take the magnetic field away, the atmosphere will be blown away by the solar wind. But people say it might take 1 billion years, so it's not something immediate. Some of the things I also wonder about, if we could live on a planet with a magnetic field, it would be really boring. Earth science would probably not exist because I couldn't reconstruct the continents. There would be no magnetic anomalies in the oceans. Nobody would invented a magnetic compass because we don't have a field. And of course, we use satellites now, but they would be very vulnerable to all the solar flares. So it's probably, if we could survive on a planet without, it would not have the civilization as we have now, or it would be very delayed. So I started off my life as a paleomagnetist and magnetism, so a lot of the stuff I do is to reconstruct continents. And this is just to show from my beloved area. So black here is Norway, and the little dot there is to show how Oslo has moved in latitude. So I told Sue, we're on 60 degrees there now, and when I come here, it's much warmer because you're on lower latitude. We had 4 or 5 degrees yesterday when I left Oslo. But you can see back in time also Norway, or part of what we call Baltica, also enjoyed tropical and subtropical latitude through time. And we do that from paramagnetic data. And you're all well known with a compass. You go out doing orienteering, it's kind of pointing north-south, but what's more important is actually the dip of the magnetic field. And these compasses have put little weights in to compensate for where you are using it on the planet. So, and if you're on the equator, there will be zero dip. So if you have a volcanic eruption, it cool down to a certain temperature, we call it Curie temperature, you lock in the magnetic field. And then you'll get steeper and steeper. On the North Pole, it was point straight down, and on the South Pole, straight up. One of the problems with the magnetic field, we only know latitude, and we know orientation, because it should be kind of north-south, these vectors, and if they're rotated, we normally, the continents could have been rotated with it. So longitude stimulated me to get in with this, first with Kevin Burke, because Kevin Burke was originally more associated with Lou and Sue here in South Africa in the early 2000s. I kind of inherited him. He wanted to do things with me, but I said, we cannot do longitude. And he said, come on, must be some way of doing this. So that kind of triggered this kind of, some of the work I will show. So just to remind me, if you want to read a book about longitude, I really recommend this. You know, you cannot determine longitude astronomically, and there was a big prize money in England. Who can solve the longitude? And he built a clock, you know, chronometer. So in the beginning, they didn't want to give him the money for sorting this out, but in the end, I think his kids got the money prize, which was quite big at that time. So, you know, longitude is a totally arbitrary thing. And its zero is in Greenwich in England. They were fighting with the French. They wanted it in Paris. So the French got a meter. They go to a museum. You can see the standard meter length. And the Brits got the zero meridian. So it's not a geodetic thing. So a magnetic field and how it's recorded is very important. Plate tectonics, it's also very important for habitability. It regulates, for instance, interior temperatures. Subduction enables recycle of volatile elements into the mantle. And it also regulates atmospheric greenhouse, either by sinks, weathering, taking CO2 out, or for instance, volcanic arcs where you have a source of CO2. So this is the biggest thermostat on the planet. But probably for decades now, nobody really knows when it started. We can describe it today, what we call modern plate tectonic. But there is endless literature when it started. And, but in some way, I think plate tectonic in some way, but the mantle was hotter. The subduction was more shallow, probably starting at about 3.5 billion. We also know we had not supercontinents, but we have some sort of assembly of cratons starting from about 2.8, and some of the African cratons, like Cap Verde, was involved in that. But some people actually say modern plate tectonic didn't start. It was only in the last 700-800 million years, for instance. That's one extreme. Okay? But then you have others that it started in Hadean on day one. You know, what's your problem? Okay? So you can find all that in the modern literature. And I still don't think we have any super good answers. One of the reasons why they have modern plate tectonics very late is that there are no evidence for blue schist before that, which is cold, steep subduction, before 600 million years or so. So this is one of these supercratons shown at about 2.5 billion years. This is a paleogeography we are very interested in, because this is actually about when we got what we call the Great Oxidation event. We got oxygenated atmosphere. We also people also argue it was the first time we had a snowball Earth, and we also have very extensive large igneous provinces. Still, we are fighting a little in which order these things are coming, but that's some of the things which were interesting in terms of. You probably also heard people talk about supercontinent cyclicity, and the oldest normally people talk about is Nuna or Columbia, different names. And then we have something called Rodinia at about 1 billion years. And then we jump straight to Pangaea. I never liked this, and it was partly influenced by Kevin Burke. He said, what about Gondwana? You go around and you see the maps by Martin de Witt and the other. Gondwana was 100 million square meters of continental crust. And size-wise, it's bigger, for instance, than some of these others, bigger than this Nuna Columbia. So we've been calling it some sort of super terrain or a big terrain. And one of the reasons people don't like it, because it really ruins this cyclicity. Because you go from this Nuna to Rodinia, about 500, and then you go from Rodinia to Pangaea, was formed about 250, 300 to get 500. Gondwana makes it problematic because it's literally sitting in between them. So just want to make the point, I think Gondwana should be considered as a supercontinent. So that was just a little background. Now we're going to linking surface and deep earth processes. And in the very, what we did develop, which not everyone agree with us, is that if you look at Earth today, so I'll just show one side of it. Near the core mantle boundary, we have something called large low shear velocity provinces. Probably something which is a little hotter, but also denser. And all the work I did with Kevin and Lou and also Sue was to point out, of course we know we have subduction, but they are kind of moving along the core mantle boundary, create some thermal instability, and you get plumes coming up, more or less from the margins. And you have another one on the other side, so these are totally antipodal. But this is a present-day phenomenon, and the question is, how long has it been like that? Has it been like this for 100 million years, 200 million years, 1 billion years? Kevin said it was related to the moon forming events, so he wanted to make it 4.5 billion years, which we have no evidence for. But we did publish a paper, and one of the other co-authors said, I said, I'm really skeptical to this. He said, don't worry, it's going to be rejected. But it didn't get rejected, the paper. It was one of those where the reviewers simply didn't know what to do, so they said, well, the literature needs this kind of stuff sometimes. And actually was no correction for the paper, which I more or less thought we should have had rejected. That's how it works. Sometimes you write brilliant paper and they get rejected. It should not be rejected, but here was kind of an opposite side. So, and it's kind of also historically linked. If you look at revolution in earth science, we talk about 3 major revolutions. It was continental drift, which was Wegener around 1910, 12. And he was pretty much ignored until you came all the way into the 60s when they discovered, already in the 50s, they had discovered the magnetic anomalies in the oceans. And also the Americans during the Second World War have mapped out with gravity all the fracture sounds. So you started to get an idea of something was going on in the oceans. And then, of course, what we call the plate tectonic revolution. Most people put it about 1967. It's a paper by Mackenzie, where he kind of it's actually for quite young Earth, Cenozoic, Mesozoic, from the Pacific, mapping out the magnetic anomalies and putting some Euler geometry. And very important, just a few years before that, somebody wrote a paper saying the third plate boundary. Well, even that was strike-slip faulting. So before that, we only have spreading and subduction until one guy in 64, hey, maybe there's a third plate boundary. Continent can slide past. And then you had today, we might laugh of it, but that made then people to develop and could put it all in a mathematical framework and run it backwards, forwards. And many, many people, and I'll show you some later, in the elderly generation, more or less stopped this. They didn't proceed from plate tectonics. Like I heard a talk by Mackenzie once, and he said, I stopped caring about plate tectonics in the 1970s. It was all in the textbooks, like it was all solved. So he did other things, okay? And I did my PhD in 85, you know, so according to somebody's heroes said they've solved everything. There was nothing to do. So, But the problem with plate tectonics is only a kinematic theory. You have these 3 plate boundaries, we have 10 big one and a smaller one, but it doesn't relate to what's beneath us, to the mantle. So that's what we wanted to do. So we wanted, very ambitious, we call it the 4th revolution, and we put his name Mantle Dynamics. So you can see now on this bar, we had this arrow into mantle dynamics. And our previous center, which was called Earth Evolution and Dynamics, this was the main goal in that center, okay? And I had hoped we solved it all, but I also realized not everyone believed our story. People are just like, you cannot call it the 4th revolution, because not everyone more or less believed in plate tectonics. Not everyone, though. My PhD advisor, he rejected plate tectonics during my PhD. So there are weird people out there still. But we still call it the 3rd revolution. Anyway, so the main thing we wanted to do was so we have this very simple, with plate, we have plate boundaries, and we had all these hotspots, and people got wild every time they found a new volcano, but they call it a hotspot, something deep in terror in the earth. And I told them, you have to stop this. And my friend Bernard Steinberger, he named a new one for every time he had a birthday. It was 50, 51, 52, etc. So I'll say we have to stop this. It can be hard to distinguish what's really deep or not. So, but if you look at, for instance, on some tomography over Hawaii, so this is from the French and Romanovich, but it's quite modern, 2014, because until this paper appeared, most people say, oh, we cannot see these plumes there. They are wobbling, and suddenly in their study, they were crystal clear for some odd reason. Don't know what they did compared to the other tomographer. But suddenly we saw these very, sometimes quite narrow, but you know, then they spread out when they hit the transition zone or the base of the lithosphere. And here you can see, I talked about these what we call large, low shear velocity provinces. You can see it's sticking quite up in the mantle of the Pacific, and then there's another one on the African side, I'll show you. But the main thing here, you can see these plumes coming from the margins here, which we think to trigger them could be subduction. Of course, my partner who took over didn't like this because he works on Mars, because we do actually perhaps see something similar. We don't have, because you can see these in the gravity, in the Earth's surface as well. On Mars, they have gravity, they call aeroid instead of geoid, and they also have some big volcanic activity, and you can see they're also distributed around. But on Mars, we have no evidence that subduction ever occurred, so then you will need another trigger. So that's why it's still out for debate, these things. So when it comes to one of these things, these mantle dynamics, we say understanding plate tectonics in the framework of mantle convection, and particularly intraplate volcanism, because many of these hotspots, if you look at plate tectonic theory, all the action is going to be on the plate boundaries. That's where you have earthquakes, that's where you have volcanism, and then you have all these what we call hotspots. They're intraplates. Some of them are very close to spreading ridges, etc., but they don't really fit in. So this is just, for instance, and also large igneous provinces was the one we started first, and here you can see them today on the present-day map. And I don't know if you, and also in Oslo, where we came from, people have been arguing there for 3 decades whether this was a large igneous provinces, because they had certain minimum criteria for size, potential mantle temperatures they operated with. But this cliff there is one of the oldest we can reconstruct. We call it Skagerrak-centered large igneous province. It's 300 million years, and it's erupted. And also the old age state that was distributed over tens of millions a year. But when they all got data uranium lead, they all single in on 299 or something. So you can see today they are spread around. So one of the things I will convince you when you actually reconstruct these things, that they will actually then start to show something which eliminate what's going on in the deep mantle. So just to a little about Alomos. So there are a number of models. These are normally for shade wave velocity near the coronal boundary, which is much better than the P waves down there. And it doesn't really matter what model you look at. This is kind of what it looks like. And so beneath the African, we have the African one, and with Kevin Coltuso, and I will come back. He was a master of acronym. This is the name of a very famous guy in geodynamics and geophysics, but I will read out what it actually means on my very second last slide or something. And then he had a Pacific one, which he called Jason. And that's the name of an also very famous scientist. So these are acronyms reflecting 2 very famous people, but I will read out what it means. But we call these large low shear velocity provinces, or LSVPs. And some of the things you can see, they are almost antipodal, 180 degrees apart, and they're prominent in every shear wave tomographic models, typically about 3%. What we are still arguing are these thermal or thermochemical reservoir. I didn't like they could be thermal. If they were thermal, they would just be pushed around. Why should they be there? Because you will see I want them to stay there for a while. And what is the origin of stability is why we started off. I'm showing this surrounded framework here. It's something Terra's Garia once showed, and I wanted to have a copy. Point out that, so you have the depth here. When it comes to what we know about the deep Earth, it's literally, we only know it in modern time, okay? From paleomag, it can actually go back in time because it tells you something about the dynamo. We can do paleointensity. But you are reliant on the rock record, and it gets less and less, and at 4 billion years, the end of the oldest known rock, okay? You can have some zircons in Australia going to 4.3 or whatever, but they are in the sediment, which is younger. So, but when it comes to what we know about the deep Earth, it's present-day phenomena, okay? And God knows, can this pattern actually be preserved back in time? So if we look at this pattern now, you will see that around Jason, you will see that, and you see how Y is sitting up there on the margin of this thing, and they're kind of surrounding. And if you look at around Tuso, the African one, they almost perfectly distribute around the margin. It's not that perfectly on there, but there is a clear relation, and then we do statistics, how close they are there, and people then want to know what is the statistical significance, so 95% can drive you nuts when you try to publish this, because people want to know the statistical significance. But anyway, to me, and also to Kevin, who was not either a mathematician or statistician, we call it this pattern, it must mean something. So, so that's why we say hotspot argue from sites to be sourced from deep. They are linked to this Jason and Tucson. And I say majority is sourced from the margin. And we call that the plume generation sound. That's also an acronym, PD set of Kevin Burke. He loved to have names on things. So we call it a plume. So we're saying most hotspots are sourced from these areas. And then the question is, how long have they been stable? And then that's where we have to switch the large igneous. But we look at hotspots there. Some of these have actually been active for 120, 30 million years, but we're looking at present day instantaneous picture. and we have to go to large igneous province and try to reconstruct them to see if we can see a similar pattern with time. And so again, I show you this picture here. There's a present day where these are the large igneous provinces we thought were well dated and from various catalogs can really be characterized as a large igneous province. And the youngest one is Columbia River basalt. The first one who made catalogs of these was an American. So he made a minimum criteria to be a large igneous province that must be bigger than 160,000 square meters, which is not very big, just to get Columbia River in there. So they had one large igneous province, okay? But it's actually tiny, and you will see later, it's the only anomaly in our maps. It's so tiny, and it could actually, this is an active subduction sound area, and it could have a different reason for this. This is also where the Yellowstone in, which we normally think about as a plume. So, this is the distribution today. Sorry, what did I do? Yeah, I also want to comment, a lot of the fun I did with Lou and partly Sue was that I came the first time I met Lou in 95, and we did the first fieldwork in. He dragged me to Madagascar first, which I hated. Unsafe, I didn't like the food. I got sick as a dog, I had diarrhea for 3 weeks, and I told him in American, it must be a better place to go. What? Yeah. Oh, what is it? Oh, did I? Oh, sorry. So there must be a better place on Paradise. At that time, we actually not looked into this trouble. We looked at Neoproterozoic magmatism, 700-800 million granites or whatever on Pan-African. And then one of the Americans said, I think we have the same rocks in Seychelles. And I said, now we are talking. So next year, Seychelles. But there they also have young Deccan-related magmatism. And on the way, we stopped in Mauritius just to check it out, hotspot island. And we also went to India as well. So we had a really phenomenal field trip. That's how it started, and we have done this many times. The last field work was just before Lou's 70th birthday in Reunion. The two of us and Ben and one of my postdocs in Oslo, again, Kulakov. And then already Lou wasn't in his best physical form for field work, so I had to sit and watch him in the car when Ben and this other guy had to run up and down and collect samples. So it was very easy field work for us. Anyway, to cut it short, if I take these present-day large igneous provinces and I reconstruct them on a map now, and now we take the present-day tomography, assuming it's been stable for 300 million years, okay? And again here now, I told you there's one anomaly, and unfortunately that's under my figure caption here now. That's another trick for young. If you have 1 out of 100 anomaly, put your figure legend there or something. If you don't want to, you mention it, of course, but I normally do this for talks. I don't have to get in. Everyone would say, hey, why doesn't Columbia River sort of fit in here? But you can see, they really fit around. So again, and here we also mapped out subduction for the past 300 million years. And so I don't think that there is these two theories for these. Either they've been stable there for a very long time, but the only way is actually maintaining them by subduction, because the pattern of subduction has been incredibly stable on this Earth for at least 300 million years. So you will see all the blue area has now, and you will see it's hardly they touch in. A little here on the Pacific, they're touching in, but almost like they're avoiding it. So you have these two antipodal upwelling and the subduction. So the subduction itself can control them as well, or be a stabilizing factor. But that's another message. So this seems to be quite a stable thing for at least 300 million years. I don't want to make it too complicated. I said we reconstruct the continents. We only get latitude, and the only reason I could show you longitude there was that we can use a hotspot reference frame, but that can only be used to about 125 million years. Then we actually also get a longitude. Here's Africa. You can see this back to 120 million years, how actually Africa has moved. And then before that, there was something me and Kevin Burke dreamt up over a few bears. How on earth are we going to do this before? And then we thought, well, Pangaea, Africa, has kind of been surrounded by subduction sound for a long time, almost like Antarctica. It doesn't really move, so it's kind of stuck there. It's basically gone northwards a little, okay? So let's use just Africa as a reference. And so all these maps were made by this way. We just kept Africa in the same longitude. But even by doing that, we saw this spectacular pattern. And of course, it has changed. You can see that for the last, so there is about 15, it's up to 11 degrees there or something. But Africa seems to be quite stable. It was part of Gondwana, was a big chunk, and then it became part of Pangaea, was a bit. So it's one of the stable. So to do this, we use a moving hotspot, then we use a paleomag. And the longitude correction here was simply, not where Africa was today, but we took it out 11 degrees. Something also called true polar wonder, complicating, I'm not going to dwell into it. That's also something we have to do for a living to understand this. So some sort of take-home message here from all this, that plumes that go to lips. So the oldest one is this flip, sorry, the 297. Columbia River basalt is 15. It's actually an anomaly, but you can, everyone except Columbia River, by doing this simple longitude tricks, show this pattern. So we're then saying that these two sort of Gavson, haven't told you yet what they mean, except two famous guys. One is the African and one is the Pacific. They must have been fairly stable for the last 20 million years. So we had that, and then there is, of course, we have hotspot volcanism, we have loud igneous provinces, which is some sort of catastrophic melting of the upper mantle, and many of them linked to major mass extinctions. Another one, which is also might come from the deepest kimberlites, and that, of course, many in this institute, or at least previously. And of course, that's the business for De Beers. So we try then to also see if kimberlites fitted this thing. So this is just a kind of a recent map, a review paper I was involved when. Of course, they are normally associated with the cratons. You can plot histogram. They're a little fake, this histogram. I'm doing better now because a lot of these loud igneous comets come from Africa and the Cretaceous. So whenever the Bears found a kimberlite, they assumed the next one was the same age, 120 or 90, and some of them are dated, some by association. And if you do an area filter, you say everything within 100 kilometer and within 10, you reduce that peak. You don't get rid of it, but it becomes much lower. So also to be careful when you do histogram, because oversampling, there's a big oversampling problem in Africa. So this was not a big issue in this paper, but so kimberlites are important. I've never seen this one. Do you know where it is, Sue? It's somewhere in Africa. Looks pretty impressive. Oh, it's in Lesotho at least, is it? We even have stamp. Anyway, I hardly knew what a kimberlite was. So Lou wrote the introduction to this nature paper explaining what a kimberlite was. And and I did my reconstructions. I only learned from that history was that when they erupt, they're full of water and CO2, and there's a big splash, and you don't want to be around it. Okay? They're not as bad as a lot of igneous province. There are very few of them in modern time. So they're quite amazing. So now I show, so this actually, this picture is actually from 2004 when I took over Kevin, but when I showed Kevin this reconstructed kimberlites, and he was already then 75 or something, and he got so excited, and he said, whoa, we're going to be famous. And I said, my God, why do you care about it? You're 75, you're not looking for a new job. And he was so excited. This was the biggest since whatever. And we got his paper published, Diamond Sample by Plume from the Cornell Boundary, and this is from one of the trips. I think Kevin is packed in, it's about to leave, so this is in the garden of Lou and Sue, if you haven't been there. So, of course, it fitted, that's why he was so excited. So I'll just show you, this is from 200 million years, and I just plotted as a line here. Now this is the African or the Tuso, and when we reconstruct these kimberlites location, which is there now, you can see them. There's also a large igneous province, the Central Atlantic Mapping Province. You see they show the same pattern. If you go to 130 million years, you can see all the Cretaceous kimberlites in Africa. We just oversampled the bits. I just showed them with 1 ground symbols. But you can see it's the same. And also we put somewhat. So now you'll see we have hotspots, we have large igneous province, we have kimberlites, 3 different types of sources of material which we can link to the continental boundary. And so this is just how we talked about it. So you have slabs, you get some terminal instabilities going up here on both sides here, because here you have the Perrine Atlantica, which we also went some years ago, and also you have the Australian ones. Now, we changed a little. We only say the very lowermost 300 kilometer are maybe are the hottest, and maybe also the denser part, and these are more buoyant, going way up in the mantle if you look at tomography. So we thought we have solved it all. So that's why we actually stopped working with this 10 years ago, but there is a whole industry out there now trying to prove us wrong. So be it. We thought we had a pattern at least. So this is from another paper where Lou was involved. We wrote some, Kevin Burke was still alive, but we thought Kevin was very instrumental in this. We wrote this review, and now you can see these antipodal features here, slabs going down, and the margin. So also been a lot of discussion, how fast do slab penetrate and reach the corminal boundary? We have reasonably estimate now that in the upper mantle, maybe they go at about 5 centimeters per year, but in the lower mantle, it's closer to 1 centimeter. If you take various models, you will see it takes about 241 million years for a slab to come down. And then you can dream is kind of moving along at the corminal boundary here. It might take some 10, 20 million years. And also the ascent, also been arguing a lot, how fast does the plume go up? A lot of models wanted to come quite slowly, take 70 to 80 million years. We are saying it shouldn't be more than 30 million years, so about 10 centimeters per year. And we have some arguments for that. So also I'm going towards the end here now, and just pointing out how seismic tomography, how this is not showing a convecting mantle. I'm just running a profile in seismic tomography over this thing, and you can actually see what it looks like when you cross-cut this with seismic profiles. So, and the question what they are, some saying these things down here are purely recycled oceanic. So we think it's a combination of some bottom layer of something more older and denser. And, but also you have oceanic material coming down, and maybe some of it is sampled on the top of this thing. Others saying it's purely oceanic crusted, pushed around by the slabs. But that would have ruined my correlation. I tried to show you this correlation between seeing in the lower mantle. If these things are randomly moved around, you shouldn't see any correlation, but they just ignore that. So I told you, to get to this model to 300 million a year, we use a hotspot reference frame to get a longitude, and then we just assumed Africa was stuck in longitude. But of course we can refine that now, and then we saw this pattern. What did we do before Pangea? You cannot do it. So I'm just going to show you a very simple, what do we do? So this is this paper, which I think is the most important. Deep matter destruction is a reference frame for movement, because we can calibrate the longitude with this method. So if I start with that, this is a 410 million year reconstruction. You're in the early Devonian. Let's say I know nothing about the Earth, it's blank there, and then I fill on the margin of this Tuso and Jason, or one Tuso beneath Africa, Jason is the Pacific. So this is my reference line, okay? And then I reconstruct my continent. But remember, I only have longitude, okay? No, sorry, latitude, I didn't have longitude. But in this case, for instance, from Laurussia, that's actually North America, had collided with part of England and Baltica, so we call it Laurussia. There are kimberlite there. You see, I've moved it now in longitude until it fit one of these lines. But of course, I cannot see. I could have moved it along here, and I tried all kind of version. Similar we had for Siberia. Of course, I could have moved Siberia to hit because these lines. And I did this for about 6 months. I was trying to quit smoking. So I sat home in Adobe Illustrator, and I did this over and over in 5 million year interval until I was happy, because you also have to get speed velocity. If you just move it to the wrong one and you have to go somewhere else, you get velocities too high, and it shouldn't be more than 20, 25 centimeters. So this became the kind of ideal. And then we can put Gondwana on here. So now I put oceans on here. When I think I know where the continents are in longitude. Now we have series can do plate tectonics, because most of plate reconstruction we see model actually kind of continental drift. They don't show you the oceanic plates. So that's also part of this, to actually build up a quantitative planet with plate tectonics. And we can do this now back to, I think we can do it to 500 million years, but you will see models published back to 2 billion, 2.5. They just run it backward like it's no problem. There are problems. I wouldn't dare at the moment go beyond 500 million years, which is young in Earth history. So it's important. So now I'm coming to the very last. So the main thing with this linking surface and mantle was to move away from plate tectonic to something new where we understand how those plumes, for instance, fit into this picture. So we had this, and now you can read what Tuso means. Named after Tuso Wilson, and he was the one who came with the third plate boundary and said, hey, things can move sideways. Nature paper. Try to publish a Nature paper on that today, hey, we have stripes before. It wouldn't go very far. And so if you look at Tuso, it's like the absolute stone of Earth's deep mantle. And then the other one, Jason Morgan, is the first one also who did the hotspot reference frame. Just as stable on the opposite meridian. And this is something Kevin Burke, he could spend a week with a lot of red wine, because he will determine what they should be. And I couldn't help him, but he came up with these. And this is printed. So now we have this picture. This is from 2004, because we wanted to move away from plate tectonics. And on this picture, you have some key figures in plate tectonics. John Dewey was the one who took plate tectonics to land, together with Kevin Burke. There's a number of papers. Dewey and Burke, they actually introduced the word Wilson cycle tectonics. It was actually, again, coined by Kevin, but John Dewey was the first author. But everyone knows it was Kevin who had this thing. And Shalal was a student of them, and they were American. And they were very important in the sorry. So I put these arrows there. So Kevin, these were very important very early on the plate tectonics. And we wanted to move away from that. I told you earlier that Dan McKenzie said, stop doing plate tectonics in the 70s because we knew everything. It's in textbooks. And in 2015, I was listening to a lecture by Schilal, and I have to show you what he showed. It's in German, that Herr Geokünstler, I don't know, some geo artist, and Herr Geojuristen, that's somebody just doing the same. The point, I look at the data, there's Wegener, okay, smart guy. And then it kind of, nothing really happened, and then it comes into viele guten Ideen. Lot of good idea, okay, that's seafloor spreading and plate tectonics. And after that, we are going to hell, okay? He gave this talk 2 hours before I gave a talk. So I photographed his slide and I commented it in my talk. Because, hey, no good ideas. And I said, sorry, I did a PhD here. I'm too late. So, but a lot of people think like that. They figure it all out. But one of the things, they never figure out how it connects with the mantle, really. How all these hotspots and things come in. So I think our contribution then, with Kevin, Lou, and myself, was really trying to go. And we spent 2 weeks with them in a field trip, which drove us nuts. Me and Lou looks sort of semi-happy. Kevin is always laughing. Because Lou called them the three wise men, and they only talk to themselves about their pioneering days in America, when they solved everything in plate tectonics. So we got a little bored with them and sat alone in the bars mostly. So I also had not only a memorial for Lou, but also Kevin Burke was important. Then my final slide, so I met Lou in 1995, and we've been friends, collaborator. He was not only a great scientist, he was hilarious. He had commands no other man on the planet can come with. He had the most extravagant T-shirts. This one I bought to him in Iceland. It's actually for Sue, but he took it over. Nobody knows I'm a lesbian. I bought another pink for him because he loved pink. So I don't know where that T-shirt got. And this is the last picture we have together. And tomorrow, if you don't know about it, it's a wake. And we can memorize him. And it's much better than going to a funeral. And we cry tomorrow. Tomorrow we can think about all the good things with Lou. And that's it. It's 10 years since I did it, so you don't know.
We have some online.
Maybe not. No. Yeah, go ahead. Great.
Yeah, great, Trond. At the time that you were finding this super fruitful, these LSVPs, there was also talk of the super swell, the African swell, that Southern Africa is now got abnormally elevated in the last 30 million years ago. How do you see that? How do you thought what has driven that?
It's probably kind of connected with it, because the main of this Africa is partly with the Southern Africa. Okay? I know Kevin wanted this to be sort of more young than 25, 30 million years. And it's, but you have a thermological there which will keep these areas elevated. Okay? But Africa is amazing in terms of what is preserved. You have the oldest of everything, you have the oldest ice, you have the oldest snowball, everything. I don't know why it's so preserved. In Africa, we have nothing. It's in Norway. Finland doesn't go rock. So, so it's probably related to this.
Yeah, the other thing that is related is all this compression tectonic on a regional scale, climaxing during the Santonian. And so in Bushmanland, where people drive thinking that the Karoo is horizontal, and you go in a trench, and you see the Karoo is like the Cape Faulkland. And you go into Free State, or in the Northern Cape, the Kalahari Beds are folded and thrusted. So the problem from our side is now trying to link this heterogenic process that also was spearheaded by our dear friend there. And he always spoke of damn it, the name. No,
Oh, you are even earlier.
he was in Port Elizabeth.
Martin de Wit.
Martin de Wit.
Yeah.
Martin de Wit always spoke about vertical tectonic, the perogeny, the calari perogeny. Now, how do we fit this phenomenon with the actual still ongoing compressional tectonic that we have in Western Namibia, in the area around Springbok, and we have all this horizontal component, which even in the Cretaceous, up in the Chippies, we have Karoo basalts underneath the Clarence Formation. And so all this linking now from my side and his side, from linking what we see in the field in South Africa that for so many years have been overlooked, to this new globe plume tectonics. So I think you are putting right. There is now starting a new page after from what I can see from our experience, and I published this now a couple of years ago with him, linking this perogeny linked to this big plume to this horizontal tectonics that we see thrusting even around the bushel. We have thrust. We have an orthosite thrusted over gravels with Acheulean axis, which would not make sense, but we link now to all these other areas where we have this horizontal component. So it's not just the anomalous stress field that we spoke before, the Wegener stress field, and now we have this orogenic component. So that is something to think about.
I think Ben has a question. Thanks, Mark.
John, can you speculate on the longevity of Tuzo and Jason? Do you really think they were formed when the moon was formed, or is it something that is linked to like more well-established plate tectonics over time?
I've done papers where I think it's pretty well proven for the last 3 million years we can, with various things, we can prove it back to 500 years. We made some. Before that, I cannot really say. So magma ocean differentiate in 1 before the moon and 1 after. Maybe it's something which related back to that. The reason why I wanted that paper to be stopped was that we have no evidence. It just could be submitted to a philosophy journal. And there are people write papers with no evidence, So they have good ideas. I simply felt we were pushing them. I was happy to go to Pavan. But we always call him primordial, in that case, it's very far back. But that's also getting a little more complicated because in those days, we were doing the chemistry and the helium and this, yes, that is really primordial. And I read a recent literature, and maybe it's not the click. You guys are probably the only one who can say anything. So I don't get any help from the economists.
What evidence could there be? No.
Of course, now we complicated up with Luke finding confidence.
One question, Scott.
That's a great talk, and and it like, I guess for me it's easy to visualize that you've got these semi-stationary low velocity zones, but when you were talking about how it seems like subduction has also kind of occurred in the same region on the Earth's surface for long periods of time, I guess that for me was a bit harder to visualize, right? Because it's a bit like subduction initiation and
Yeah.
other things are a bit more like almost a stochastic
Yeah.
process, right? And
Yeah.
like, I don't know, have you thought about
This
that?
is, when I say the world has been in this comes from plate models. So
Okay.
we think we have things, and it's not from my plate model. I take somebody's own plate model, whatever they do, for the 300. But it's kind of forced into this pattern in somewhere. Yeah. And I know all the trouble, I'm going to start those productions and all the trouble with that. But what we know, we don't. If you look at them today, there's hardly any slab, whatever, where has actually penetrated the windows. And I think if they try to pen on top of them, there is so much buoyancy that they will probably never do. But that doesn't stop modelers. They crash them in the middle and they flip apart and hallelujah. And also viscosity, but viscosity is a trick. If you make it stiff enough, they will never move. Yeah? If you make it like waterish, they move. But then I have trouble as well. If the viscosity, if they're very flowable, if you're going to get some subduction, then you have no strength in the slab. How are you going to push them? So you need a certain stiffness of these things as well. But there isn't that many really trying to give us. It's literally only one word. Because they're very volatile. And sometimes some people, they feel it was not there rightly. They invest a lot of time and energy trying to figure it out. Actually, most scientists are driven by some models. We either try to fit it in or reject it. And sometimes we get a good idea and we have something else. Okay? Geology is very model driven. We actually rules, okay? In all ways. And we try either to fit in or we say, it's nice, totally out. Okay? It's must be wrong. But it's easier to criticize when you come up with some knowledge.
Any more questions? Yes, Steph, go ahead.
It wasn't a question, it was just an observation. I was reminded looking back at the honours class that they were actually in the third year class last year, which I think was Lou's last lecture. And the lecture of this and Sue helped. So you last lucky ones.
So we've got
Oh, sorry. Go ahead.
Yeah, I wanted to ask what exactly kimberlites are and how they fit in with everything, because I don't understand the relevance of kimberlites in what we're talking about.
Well, we think, first of all, we think kimberlites are broad bolts. And not everyone agree on that. We also think it's some pots for buoyant material and brings them up. Yeah? It takes a lot of, and it brings diamonds. They're plumes are elevator and they have to go very fast. But I'm not an expert to describe exactly what a kimberlite. As I told you, the blue grows big was my mantle. I'm a geophysicist. Do you want to explain what a kimberlite is called?
Probably the best.
Well, it's a low volume melt that comes up from the base of it's formed kind of at the base of the lithosphere and brings up diamonds and other mantle material, and no one really knows how they initiate. Work by Andrea Giuliani's paper, Trond cited, and also Graham Pearson and others. They found some kind of common reservoir in the mantle below in the sublithospheric mantle that suggests that's a common reservoir for kimberlite formation. But yeah, so it's somewhere between there and the base of the lithosphere that they melts kind of form, and then they, as Trond said, they come up super fast, right? And so they're very explosive. And because they're explosive, they can bring up pieces of the mantle on the way up. So they're like the Uber service for chunks of the mantle coming up to the surface.
And just to complicate it, you read the latest Nature paper on this issue where they come from. They all relate to the initiation of sequence spread. It's an insane paper. It's in Nature. Where they correlate the opening in the South Atlantic, the opening was about 130 million. Then you have that big peak rotation there. There was some sort of related to this same what to do and modeling. And then they did that back to 1.5 billion years and said, oh, we have a reasonable correlation when things started to spread and It's absolutely nonsense.
Well, there's also kimberlites in North America that Larry Heeman and others related to
Yeah.
hotspot trades.
Yeah, yeah.
So they're not
Yeah.
all,
No.
I don't agree that they necessarily see false.
No, no. No, but it's sort of a secret. But actually, the only place you can do it is actually the South Atlantic, because you have that time. But because they counted so many of the kimberlites, when we did it worldwide, it still came out with a good correlation. But if you took out just those in South Africa, then the whole thing falls apart. But absolutely no. Some kimberlites are 500 million before, some are 200 million after, and it's just a trade with number. That paper took 2-3 years to get through. Adrian was really, when we was reviewing our papers. You should refer to. We just put that one. There's a lot of weird things. They always say, hate modeling. They say, hey, you've been modeling. We plotted all these here chemistry plots. Isn't that modeling? No. It is, yeah. Half. Half and half. Half and half. All right.
Hey, any more questions from students? Anyone? Online? I don't know. I can't see online. Okay, great. Well, I'd like to thank Trond once again. And in about half an hour, we'll head over to the PG Club if anybody would like a more social interaction with Trond. He does enjoy his whiskey, so.
That's like you. I don't drink very much. I don't smoke either. I would say that tomorrow as well. But I was in Namibia with a postdoc of mine, and we had met Sue and Blue, and we had 1 week to kill, and she said, why don't we go to your? We didn't have mobile phones. It was on the normal phone, and she talked to Lou, and I could hear. She asked, can I bring my friend Trond there? And I could hear Lou, does he smoke? He said, yes. Does he drink? Yes. Excellent. Go away. That was the only 2 criteria. To come and sail with me. You did both accepted it.
Also, if anyone has not RSVP'd for tomorrow, you still can. And we'll see you at the memorial for the, and it will, there are DJs coming, so towards the end it will turn into a party, as I think we would enjoy. So,
Thank you.